Okay guys, time for our next video lesson. This one should be really enlightening in why things are first order, second order, zero order, the reactants. It's going to help you really understand why something would be important to the rate or why it wouldn't be important to the rate or why it would be super important to the rate. So in order to understand all of that, you have to understand something called reaction mechanisms. And essentially what a reaction mechanism is it shows the actual steps that the reaction takes in order to produce the products. Okay, if you take a look at this top equation up here, that is the overall equation. That equation tells us what the reactants are, NO2 and CO, and it tells us what the products are, NO and CO2. But it doesn't tell us how they react. Okay, in looking at this, you might assume that NO2 and CO just boom hit each other and all of a sudden they become NO and CO2. But that is not the case. And what you see here are what we call elementary steps. And essentially they're the steps of the reaction. Okay, so they're the actual steps that are undertaken in order for this reaction to proceed. I like to use the example of, say, baking cookies. If you were going to bake cookies, you take all your ingredients, those would be your reactants, and then yield the product ultimately would be cookies. But just taking all the ingredients and shoving them in the oven doesn't make the cookies. You have to take the ingredients and mix them. You have to make cookie dough, and then you take that cookie dough and you put it in the oven in a second step to cook it and become the cookie. So that's really what we're looking at here, is the fact that we're going to have steps to most reactions. Now some reactions take place just in one step, but most reactions have multiple steps. You're never going to have to figure out what the steps are. They're going to be given to you. You just have to know what to do with them, really, and how to analyze those steps. So for this problem, we knew the reactants were NO2 and CO, and you can see the two steps of the reaction. What actually happens in this reaction is two NO2 molecules. So you can see this one and this one. They collide with each other, and they form NO3 and NO. Now it might seem odd because NO3 isn't even in the overall equation. Okay, NO3 is a special product that forms in the middle of a reaction, and it's called an intermediate. Okay, intermediate. You'll see that word somewhere later on in your paper. The intermediate's kind of like the cookie dough I referred to before. It's something that has to be made, but it's going to get used up, okay, and reproduced. So your intermediate, you can see in step 2 is here. It reacts with the other reactant, which is CO, and it forms NO2 and CO2. So you can see the steps of this reaction actually play out. And again, I'm not going to give you an overall equation and tell you to tell me what the steps are, but you should be able to look at the steps and be able to tell exactly what's going on. Okay, so those are the steps of this reaction. The other nice thing about having the steps of the reaction, as you remember from Hess's law, is that we can actually take these two reactions, add them together, and get an overall equation, get the same overall equation that was shown up earlier on your page. So if I take all of the reactants, so there were two NO2s from the first equation, plus an NO3 and a CO, that'll form NO3, NO, NO2, and CO2. And then I cancel things out that can cancel. So what do we got here? We got an NO3 can cancel. I've got one NO2 on this side. I've got two over here. So that'll just lose one of them. And look what we're left with. NO2 plus CO yields NO plus CO2, which was that overall equation. So your steps should add up. And again, this shouldn't look terribly unfamiliar to you because it is the same thing as Hess's law, or the same idea as Hess's law, that if you can find steps that lead to an overall reaction, then those steps can be used for other things. Okay, so that's what we're looking at for our overall reaction. Now, you might be wondering what part this plays in all of this kinetic stuff, and we're going to get into that in just a second. Let's go ahead and try a quick practice problem just to make sure you're understanding what exactly we can do with these steps. So it says it's been proposed that the conversion of ozone to O2 proceeds via two elementary steps. Okay, so these are the two steps. So this is step number 1, and this is step number 2. And it says write the equation for the overall reaction. So to do the overall reaction, I'm going to add both of these steps together. So I have two O3s plus an O, right? I'm doing all the reactants, and then yields all the products. So 3 O2s plus an O. The O cancels. So the overall equation is 2O3. O3, by the way, is ozone. Yields 3O2. Okay, so that's your overall equation. And then they said, what is the intermediate? So in this case, only one thing even canceled out. So the intermediate has to be the one that canceled out. We will get to problems with catalysts. We'll have to be a little bit more specific. But in this case, the intermediate, again, is the substance that's formed in one step and then consumed in another step. So the fact that we make it only to then use it in another step makes it an intermediate. Okay, so that is the basic idea of the mechanism steps. Now, how does this pertain to kinetics? Well, if you are looking at the steps of the reaction, one of those steps will be considered what is called the rate determining step. Okay, the rate determining step. And you can see by the definition there on your paper, it's the slowest step in the reaction, and it will limit the speed of the reaction. Okay, there's one part of this reaction that is considerably slower than the other parts of the reaction. And because it's considerably slower, it will completely dictate how much time is taken for this reaction to take place. Now we're going to do two different types of problems. One type of problem, they are going to actually tell you which one is the fast step and which one is the slow step. So if you look at this example that I have here on the board, this is telling you step 1 is the slow step, step 2 is the fast step. So therefore, since step 1 is the slow step, step 1 is what we call the rate determining step. RDS for short, I always abbreviate it. So that's the step that is going to be responsible for how fast this reaction takes place. And because we now know the step that's responsible for how fast the rate is going to occur, what the rate of this reaction is going to be, we actually have an easier way to figure out rate law than actually calculating it out. If we know the rate determining step, we can use that rate determining step to actually calculate the rate law. And here's how it works. First of all, we only care about the rate determining step. So step 2 really doesn't matter to me, okay? What I'm going to do is I'm going to look at my rate determining step at the reactants only. Okay, remember kinetics is about reactants. So the reactants in the rate determining step are NO2 and NO2. So we're going to write our rate law based on that step. Okay, so our rate law will be rate equals K. The downside to this method for finding rate law is it can't find K. Well, that's the one bad thing. But it will give you your orders and what reactants matter. In brackets, you're going to put, again, we're only looking at the rate determining step. Put the reactant, okay? And so we've got one of NO2, so there's one of those, so an exponent is 1. And then I've got one of another NO2, like so. Now we really probably wouldn't write it like that. There's 2 NO2s, so instead we're going to write it as rate equals K times the concentration of NO2 squared. And that is the rate law for this reaction. So you can see NO2 from the overall equation was represented. Now CO wasn't. What does that mean about CO? Well, technically, I could write it in here, but if it's not part of the rate determining step, then it doesn't determine rate. And if it doesn't determine rate, its exponent will be, I hope you said 0, right? So you can write it on there if you want. But you see now, why CO has an exponent of 0? It's not part of the step that matters. It's not part of the slow step. Okay, so again, the slow step is the rate determining step. And if you know the slow step of a reaction, you can actually use it to determine the rate law. Okay, fascinating technique. But again, sadly, it doesn't give us K. But most of the time, or a lot of times, we want to find the rate law so we know the exponent so we can see the effect of that reactant on the rate. So it still serves a lot of purpose for us. Okay, so that is one type of problem. Now I want to show you one that's a little trickier. Okay, again, same type of problem. You see they've given us the 2 steps. They've given us the fast one and the slow one. They've given us the overall equation. They didn't have to give us the overall equation. We could have figured that out ourselves just by adding, but they told us. So you see the rate determining step. Maybe circle it, highlight it, something for yourself. Make it stand out to remind yourself that this is the one that matters. Okay, this is the one that's going to determine the rate. So you're going to do like we did in the last problem. You're going to say that rate equals K times the concentration of the first reactant in the rate determining step is X. There's only one of them, so it's to the first power. And then the second reactant in this problem is B, and it's to the first power. Okay, now, the reason why I say this problem's a little harder is some of you might say, okay, there it is, there's my answer. It has one X and one B, because that's what we have in that step, so it's going to be raised to ones. It's the rate determining step, so it's the only one that matters. I'm all done. Well, there's a problem. If you look in the overall equation, take a look right here, the overall equation, look at the reactants. Is X a reactant? And of course right now you are answering no, it isn't a reactant. If you look at what X is, X was made here in the first step, and X was consumed here in the second step, which means X is an intermediate. And intermediates cannot be in the rate law because they are not part of the overall equation. So here's what we have to do. First of all, when you're looking at your steps, I would always look first to see if there's an intermediate, and I would circle it for yourself so that you're paying attention to the fact that it's an intermediate. You know that this right here can't be in the rate law. However, that intermediate is important to the rate of this reaction. So since this intermediate is important to the rate of this reaction, it is now important what made that intermediate. Okay, so not only is the X plus B part important, not only are we going to include that, but now we have to look back here and see that X was made from A and B. Because X is part of the slow step, we're going to have to include that A and that B in our rate law. So instead of X, we are going to replace X with what made it. Again, instead of X, we're going to replace X with what made it. So now if I simplify, I'm going to have rate equals K. There's one A, so that'll be A raised to the first power, and then there's two B's. So it'll be B squared. So again, keep an eye out for those intermediates. They can't be in the rate law. Write that down for yourself. Intermediate cannot be in the rate law. And then you can write down for yourself that you need to replace the intermediate in the rate law with what made that intermediate, which was an A and a B. Okay, so that's the second type of problem, a little bit more challenging than that first problem because we had to deal with the intermediate. Now, there is another type of problem that we're going to see, and you notice in this one right away, we've got steps, we've got our overall equation, but they have not told us which one is the fast and which one is the slow step. And because of that, you might feel like, well, how do I know? What am I supposed to do with this if I don't know which one is the fast step and which is the slow step? But if you notice, that's not what the question's asking you to do this time. It's not asking you to write the rate law. The problem actually gave you the rate law. Here's the rate law for the reaction. Okay, it's K equals NO squared times Br2. Now remember, this overall equation doesn't tell us anything about the rate law other than what reactants we could potentially have. One of these two steps is leading to that rate law. Okay, what we can do is figure out which one is the rate determining step based on the fact that the rate determining step should give us this rate law. They told us that this is what the rate law is supposed to be. So what we're going to do is two little scenarios. We're going to say if step 1 is the rate determining step, okay, we'll do the work. If step 1 was the rate determining step, then based on step 1, rate would equal K times the concentration. It's only one reactant, but it's 2 times. So the concentration of NO, and that would be squared. Okay, if step 1, if is a big word, if step 1 was the rate determining step, the rate law would be rate equals K times NO squared. Does that match? No, it does not match. If it doesn't match, then that means step 1 is not the rate determining step. Now by inference, you know that that must mean step 2 is, but let's confirm. Okay, so we're going to say if, because we still don't know, step 2 is the rate determining step, then let's write what the rate law would be. It would be rate equals K times the concentration of the first reactant in step 2, which is N2O2, times the concentration of the second one, Br2. And notice there's ones in front of each one of those, so the exponents are both ones. Now, this rate law right here still doesn't match, but that's because we're dealing with an intermediate. See the NO2 that right now we have listed as a reactant? It can't be a reactant. It's an intermediate. It was formed in step 1 and consumed in step 2. So it can't be an intermediate. So, I'm sorry, it is an intermediate, so it can't be in the rate law. So I need to replace this with what made it. Okay, so I look back up here, see where NO2 was made. It was made by 2 NOs, which would be represented by NO squared because of the 2 NOs. So my final simplified rate law would be rate equals K times the concentration of NO squared times the concentration of Br2. And if you notice, that one does match. So that means step number 2 is the rate determining step. Okay, and that's really what the question was asking you to do. For some reason, I don't have the question on mine, but I believe you have the question on yours. Yeah, it says determine which was the slow step. The slow step's always the rate determining step. Now again, you have to really be thinking about what you're doing. So if any part of this was confusing at all, you definitely need to go back and rewatch it again. Okay, there's 2 types of problems. Problems that tell you the slow step, what the slow step is, and you write the rate law from there. And then problems that want you to figure out what the slow step is when given the rate law. So both scenarios, they give you all of the steps. You just need to learn how to use that along with the intermediate to get all your information correctly portrayed for the problem.